All right, hello AP students. Welcome to your Unit 8 weak equilibria, weak acid, weak base equilibria walkthrough of a problem. We're going to go through a conceptual on weak base equilibria, and then we're going to hit up a weak acid AP long FRQ. So I highly recommend going and watching both, but you are welcome to look at the description, and I will put the timestamp for when the AP question starts. So question number 7 on page 3. What we have is we have a 0.01 molar solution of morphine, and we know that the pOH after, let's put it this way, of the mixture, okay, is 3.9. So quick hint, if they give you the pOH and they don't specify, like they're not saying initially it was this. If they just say, oh, the pOH or the pH of the solution is this, that's an indicator that this is the pH or the pOH measured once equilibrium is reached. Okay, unless they specify, hey, this is the pOH specifically for the initial conditions, and then you added something, you can pretty safely assume that if they give you a pH or a pOH of an entire solution, they're saying that, okay, once equilibrium reached, this is what we get. Okay, and so that will be key in understanding how to use the prompt information to fill in ice tables and equilibria problems. So we're told that it has a pOH pretty once equilibrium is reached of the solution of 3.9. Calculate the KB and the PKB, the potential KB, right? PKB, P means potential of. For morphine, let MOR and HMOR represent the conjugate pairs. The reason they do that is that morphine is a really long, complicated molecule, so why write it? So for our purposes, I just filled in the ice table with the information we know, okay? KB and KA, weak equilibria, is always put in terms of H2O and reaction with H2O to isolate the acid and the base behavior. And since almost like all acid-base reactions are conducted in water, water is the environment. And in this case, for our mathematical isolation, water is also one of the reactants because it is amphiprotic and therefore can act as either acid or base. So what we do have here is that water is acting as the acid and it's liquid. So I just like crossed it out in the ice table because we never include solid or liquids. And we have water donating a proton to morphine. Now, morphine's initial molarity is 0.01 molar. We know that it doesn't produce any conjugate pairs in the beginning until it actually reaches equilibria and reacts, exchanges a proton with the water. So this is kind of our initial setup based off of the information given in the prompt. So what you'll notice quickly is you can't really fill out the ice table any further based on the prompt information, or so you think. Now, the prompt does give you pOH once equilibrium is reached, pOH of the entire solution, okay? So if I know pOH, then I can actually use logarithmic manipulations and find the OH concentration at equilibrium, okay? So what I do then is I say, well, that's going to be equal to 10 raised to the pH, which is 3.90, 2 sig figs, okay? So I get a value then of 1.26 times 10 to the negative fourth molarity for the concentration of OH minus at equilibrium based on the pOH measured at equilibrium, or, when the solution had been standing for a while. And notice I have I really should be in 2 sig figs, but for right now, I'm actually going to just mark it because I don't want to cut off my sig figs too early in the calculation process. So I'm going to keep it as a note to myself. I need to be in 2 sig figs. Okay. So now that I know my equilibrium of OH, I can kind of fill in more of this table. I can say, well, I know that my equilibrium for OH is 1.26 times 10 to the negative 4. Which means that I have had a change of 1.26 times 10 to the negative 4, which means that in a 1-to-1 molar ratio, I've also had an additional 1.26 times 10 to the negative 4 HMOR, conjugate acid morphine, which means stoichiometrically speaking, I have used up 1.26 times 10 to the negative 4th molarity of the original morphine in solution, okay? And so what happens is then I filled in this table and get 1.26 times 10 to the negative 4 and 0.010 minus 1.26 times 10 to the negative 4 is 9.87 times 10 to the negative 3. Okay. And so from this, all right, from this, I'm able to now plug into my KB expression. Okay. So my KB expression is the product ion. So it's HMOR concentration, conjugate acid times the conjugate base hydroxide ion raised to their respective molar coefficients, which is 1, divided by the reactant, which is morphine concentration raised to its respective coefficient, which is also 1. And what we get is 1.26 times 10 to the negative 4th times 1.26 times 10 to the negative 4. So I'm just going to square it immediately, all over 9.87 times 10 to the negative 3. And you get a KB value equal to 1.6 times 10 to the negative 6. So if I have a small KB value, that means I am working with a pretty weak base because I'm getting not very much ion production at all. Okay. So how do I translate to KB? Well, KB, the PKB is equal to negative log of KB. So I simply do negative log of 1.6 times 10 to the negative 6. And notice I did report in my sig figs of 2, all right, for my final answers. So I get one negative log of 1.6 times 10 to the negative 6, and I get a PKB of 5.6, okay? So, and the higher the PKB, actually, the weaker the base behavior. So it's the opposite pattern that we see with plain KB. All right. So that is your conceptual on KB weak equilibria. You would follow the similar process only now with respect to Ka for the problem above regarding weak acid equilibria. And let's go ahead and hop to the long FRQ. So question number 2 actually it's a short FRQ starting with page 7. So here we have the following information about a weak acid, 2 weak acids actually. And we are told that we have HOCl and HOBr. And you're going to use this information to answer questions I and 2I. Remember, if they give you a data table, they really don't want you to stray. They want you to use it, okay? So which of the 2 acids are stronger, HOCl or HOBr? Well, when you look at this, you notice that the Ka of HOCl is greater than the Ka of HOBr. And we know that the higher the Ka value, the better the acidity and better acid, or what I could say is ion production. So to answer this question, you would say that HOCl is the stronger acid because it has a greater Ka, which means it produces more ions, or it ionizes more, produces more ions, okay? So draw a complete Lewis electron dot diagram for the acid that you identified in part A. So remember with the AP exam, if you were to get I wrong, but you followed according to your I and you drew it correctly in 2, even if your I was wrong, you wouldn't lose the point in part 2 as long as you followed through correctly in your logic. So just want to put that out there. And don't forget, hopefully you have not forgotten how to draw Lewis structures from unit 2. It's a big, big, big concept, right? And what you should get is for this, you should get HOCl and Cl. Remember that we always calculate our total valence electrons first. So we have a total count of valence electrons of 1 from hydrogen, 6 from oxygen, and 7 from chlorine, which gives us a total of 14. So when you draw Lewis structures, you of course draw the skeleton first. Well, I've used up 4 there, so I have 10 remaining to distribute. Hydrogen has its duet. It has access to 2 through that single bond, so we're fine. So I'm going to start by filling in the terminal atom. Okay, chlorines are pretty much, halogens are pretty much always terminal, unless obtusely written as an center atom, because it's like the only halogen are surrounded by like the same several terminal atoms. Like, but for the most part, halogens, column 17, are almost always the terminal atoms and can never, ever make multiple bonds. So we fill in the octet with the 10 remaining electrons after drawing the initial skeleton. And that means I have 6 that I just used up. So I have 4 left. So I distribute now to the oxygen in the center. And now I check, well, do I have an octet for each one, barring hydrogen? And I notice immediately, well, chlorine has an octet and with 3 lone pairs and a single bond. And now my oxygen also has an octet with 2 lone pairs and 2 single bonds. And I've used up all of my possible electrons, right? So I went to -4, then -6, then -4, which gives me 0. So I know that this is the correct Lewis structure for the molecule that I identified above. Okay, so hypoiodous acid has the formula HOI. Predict whether HOI is the stronger acid or a weaker acid than the acid you identified in part A. Justify in terms of chemical bonding. So HOI would look like this. Okay. And what we see is, well, it has a pretty similar structure, but the change here is the actual element itself, the atom itself of I versus chlorine. So immediately I need to go through and like, well, what's the difference between I and chlorine? Well, I is in N equals 5. It's in energy level number 5, whereas chlorine is in energy level number 3. Well, we know that the higher the energy level, the weaker the Coulombic attraction. So we have a weaker Coulombic attraction being experienced here. Okay. And we also know that as you go down a column, electronegativity decreases. Remember the concept, all roads lead to fluorine. So chlorine, on the other hand, is closer to the position of fluorine, and that means its electrons are held closer by its protons. It's just a better ratio, and distance is just super powerful, right? According to the Coulombic attraction, force of Coulombic, we know that it's some constant K times charge of 1, charge of 2, all over R squared. That R squared shows us that distance is incredibly powerful at weakening exponentially the force of attraction. So you know that this would, relatively speaking, be a higher Coulombic attraction because you have less distance. Okay. And if you have a higher Coulombic attraction and you're in a higher energy level, you also know that you, on the periodic trends, have a higher electronegativity. So when we look at this, then, if the goal of being an acid, right, the goal of being a good acid is that acids donate, okay, donate their H plus ion. Well, that means that the better the stable, or I should say it this way, the more stable your conjugate is, the conjugate base, okay, the better the acid. Because obviously an acid isn't going to give up its H plus if it's super destabilizing to it. So what we're looking at here is, well, which one of these halogens is going to produce a more stable conjugate base? And what we know, according to our lecture on the role of structure determining acidity, is that greater electron withdrawing or higher electronegative atoms in a acid structure will stabilize, okay? Will stabilize the conjugate. So we would say then that the conjugate base of chlorine, okay? The conjugate base of HOCl is more stable. The conjugate base of HOCl is O minus Cl and is more stable, okay, due to its high electronegativity. And another way to put it is electron, right, withdrawing. Its electron withdrawing capabilities. One second. Okay, therefore making it a better acid. And let me move some things around because I think I wrote too big. So let me move this around. Okay, so the conjugate base of HOCl is O negative OCl minus, and this is more stable due to its high electronegativity, electron withdrawing Cl atom. And thus it will be a better acid, okay? Or a stronger acid, I guess you could say. Oh, stronger acid. Than HOI, okay? So the conjugate base of HOCl is negative OCl, and it is more stable, okay, due to its high electronegativity or electron withdrawing Cl atom, and thus it will be a stronger acid than HOI. So that's kind of how you should think about this problem, and hopefully much quicker than I said it or wrote it. So next step, write the equation for the reaction that occurs between hypochlorous acid and water. So here you're just being asked to write, okay, the reaction. So they didn't specify whether they wanted the net or the full. So I'm going to write you both. So the standard reaction would look like HOCl, aqueous, right, reacts with water, liquid to produce, okay, and this is a weak acid because we are quantifying it in Ka, to produce an equilibrium OCl conjugate base, aqueous, and hydronium ion aqueous. Okay, that would be the complete reaction. So I'm going to say complete. If you wanted to, or were asked to write the net, this would be what the net would look like. It would just be HOCl aqueous, only including the relevant, well, they're kind of all, I guess you could put it this way, isolating it to the compounds of focus, okay? And then it's an equilibrium with its OCl minus and ion production, H plus ion production, because technically H3O plus is just showing us that water's carrying that H plus. So we would isolate it to H plus for the net ionic, just parsing it down to the critical ions involved in particles. So either one would be acceptable by the AP. So here we have one more, and then I feel like this was definitely a long one, but whatever. I think this got mislabeled. A 1.2 molar NaOCl solution is prepared by dissolving solid NaOCl and in distilled water. The hydrolysis, so remember hydrolysis reaction is an ion plus water neutralization, okay? Reaction OCl minus plus H2O liquid in equilibrium with HOCl and OH minus occurs. Write the equilibrium expression, okay? That's easy. You should be like, oh, easy money in the bank, right? KB is going to be equal to the product So HOCl of the forward reaction raised to their respective stoichiometric, okay? Molar ratio times OH minus all over the reactant. Well, we don't include water because again, it's a liquid. So that's like saying a 1, so we don't include it, okay? So then we just do over the molar concentration of the reactant OCl minus, okay, raised to its respective stoichiometric power, and that is Kb expression. Then you're asked to calculate the value of equilibrium at 298 Kelvin for hydrolysis, which is, by the way, the standard temperature, where they specify temperature, remember, because K is impacted by temperature. But standard K values are always calculated and determined at room temperature or 298 Kelvin. So what you would see is that you don't have that much information, unfortunately. So what you do have, though, is in the memory bank, you do have KW. And from the work above, you also have KA because you were given KA of HOCl. And in your problem, you have HOCl. So what you can do is you can say, well, I know that KW, which is 1.00 times 10 to the 14th, is equal to KB times KA. Okay. And I know that the KB, well, what's the acid that I can include in my equilibrium expression? Well, it's not water because water tends to be this like, right? In our Ka and Kb questions, it's not considered the essential reactant. It's just serving the role for us to allow us to isolate the acidity and the basicity of a specific species. But the real acid involved and the one that's actually written in your Kb expression is the conjugate acid HOCl, right? So we've already done that work. We've been given that data. We know the Ka, the level of acidity of HOCl, right? And so what we're being asked though to solve is for Kb. Well, that means if you know Ka of HOCl and you know Kw because it's a standard kind of constant almost, like it just kind of becomes its own constant because it's just such a standard, then you can solve for KB. Okay, so I'm going to translate from my data table that they gave us in the original prompt. Notice you're being constantly asked to go back to the data, is 2.9 times 10 to the negative 8th. And they even specified at 298 Kelvin. So that's a really good hint that all things align to you using this data point. So 2.9 times 10 to the negative 8th is equal to my Ka. So all I do now is I plug it in and chug it out, right? This is a plug and chug. So I say, well, I know then that Kb is going to be equal to Kw all over Ka, okay? The relative strength of my acid conjugate versus my base conjugate of the same foundational species, all right? And when I plug that in, I get a value for Kb is equal to 3.4 times 10 to the negative 7th. So that means the ability of my OCl minus base, okay, deprotonated version of the HOCl times the acidity capabilities of my conjugate acid HOCl for the same foundational species, just differing by one proton. Those values, Ka and Kb, together add up to the Kw. Okay. Another way to put it is that the pH and the pOH, the potential of base production, the potential of high acid production is equal to 14. If you wanted to turn it into a logarithmic scale, they all connect, right? So you're kind of looking at two sides of the same coin and you know that they have to add up. Its ability to be basic and equilibrium has to be partnered with its ability to be acidic and it has to total up to the sum. All right. So I really hope I didn't confuse you more, but that's kind of what we did here. If all of that didn't make sense and I rambled on too long, just look at the numbers. The numbers don't lie. Look for the trends in the numbers. Look for the patterns in the numbers. And ignore my explanation if that just made it worse. I'm sorry. Now we're being asked to calculate the value of OH minus in the 1.2 molar of NaOCl solution at 298 K. Well, here, okay, you are now being asked to consider, okay, an ice table, right? You're in equilibrium. So what would be the OCl minus? Well, you need to set up an ice table equilibrium. So you're going to say OCl minus plus H2O, which by the way, we won't obviously include, goes to HOCl minus, or is in equilibrium in producing HOCl minus and OH minus. Okay, so you would then set up your ice table. And again, I always write this far too big initially. Okay, so then you set up your ice table. Oops, that's very crooked. And you know that at the beginning, you have a concentration of 1.2 molar. So that's what you're told of OC, okay, L minus, that is brought by the NaOCl. Here, Na is a spectator ion. It just is kind of bringing the important ion that actually reacts with the water, okay, that actually does an acid-base interaction with the water. Spectator ion. So you would have a concentration of 1.2 OCl minus, because you know for every NaOCl, you are going to produce 1 OCl minus, okay, in molar ratio. So that's why I could say that the original concentration of 1.2 molar NaOCl is my initial concentration of OCl minus. I do not care about the water. And of course, I start with initially no ions produced because I don't have a Chi-ion ion present. I didn't dump this into a solvent that already had an ion present. So I'm just going to use standard ice table practices. Okay. And I know that stoichiometrically speaking, I'm going to use up 1x, and then I'm going to produce 1x molar ratio, okay, of each ion. So what happens is I see that, okay, I have 1.2 minus x and x and x. So when I plug this into the KB, oh, sorry. Yeah, when I plug this into my K equilibrium expression, and here I'm going to plug it into my KB expression because that's the information I know. And I'm doing this in terms of the production of OH minus, which is a base reaction, right? So, and with respect to OCl minus, so I see the KB expression is going to be equal to HOCl times OH minus all over OCl minus. Notice you are using the work from the part above in part 1. Okay, so it's almost like it's trying to guide you. All right, and what I get is I get x times x all over 1.2 minus x. So quick note, we can use here percent ionization, okay, where that we say is if the percent ionization is less than 5% of the initial concentration, all right, is less than 5%, we can assume negligible, that the change in I definitely misspelled that, negligible, that the change in your original concentration of base is so minimal because you have such a low KB value, you have such a low ion production that calculating the actual change in the original initial amount would be like calculating a minuscule loss. So here, what we notice is trick of the trade is, well, is your KB, okay, is your KB significantly less in value than your initial concentration of base or acid. And for us, it's base because we're talking about OCl base perspective. And what we see is RKB has a value of 10 to the negative 7. Okay, 10, that's the value. And our OCl minus has a molar concentration of 1.2. You are definitely looking at a problem where you have more than a power of 6 difference between the KB and the initial concentration, which means you are having like a millionth of a fraction of your OCl minus actually producing ion. So as far as calculating the change with respect to the initial OCl minus, we're just going to assume that negligible because it is so minuscule, it doesn't really matter. Now, obviously, every ion counts when looking at the product, the production of ion, but as far as the subtraction from the initial, it doesn't really matter. So what happens is we assume negligible, and what this becomes really is x squared using that 5% ionization negligibility rule over 1.2. And that is equal to, from your work above, where we found KB, that is going to be equal to 3.4 times 10 to the negative 7. And you simply just solve for x. And x equals, okay, 6.4 times 10 to the negative 4th molarity, and your x is your concentration of OH minus. And that is how you would solve this problem. Okay, so notice the AP questions tend to guide you in information before you're going to probably use in the next sub prompt or sub question, okay? So finally, a buffer solution. Oh, we haven't actually quite gotten here to buffers. So let's go ahead and stop here. We will save this for later when we talk about buffers, about weak acids after our discussion on titration curves. And I will be introducing a new equation for you in order to calculate what happens when you have the presence of an acid and its conjugate and how does it affect its response, okay, to addition of a titrant. But that is a sneak peek and I've talked too much. So hopefully you feel a little bit more clear on this walkthrough. Big idea, trust the numbers and trust the prompts. They guide you in the AP question. Also, if you're a little confused on the process of how did I go from this to this to this, I highly recommend that you listen through this and not write down the problem, but you write down the process as a flow chart. No numbers involved, just terms. Start with ice table. Look for this. Apply percent ionization if this, right? Give yourself a flow chart of thinking if my explanations become way too wordy for you and you just get confused, break it down. Okay, for yourself. Do what you need to do to be successful in this class. So best of luck, everyone. Good job.